Good morning, everyone. Welcome back. Today we're going to be going over differential equations. So on our second to last video, we're almost through all of the content. Tomorrow is Maclaurin series, and then that'll be everything. But today, differential equations. So we're going to learn what a differential equation is, the most basic ways to solve very simple differential equations, which is essentially just integration. We're going to learn how to separate variables and integrate. We're going to learn about the integrating factor and how to solve homogeneous equations using the substitution y is equal to vx. And I believe we're also going to learn Euler's method. That's the other one. Okay. So we have four different differential equation solving techniques that we're going to learn, and one approximation technique, which is Euler's method. So with that said, I'm going to get started. So what is a differential equation? Well, a differential equation is very simply an equation that contains a derivative in it. And in the IB, these are always going to be first derivatives. You're not going to have second derivatives. And there's only going to be one derivative in the equation. You're going to have the derivative possibly multiplied by something equal to something else. And those equations can be very simple or they can be very complicated. The easiest ones to deal with are the ones in the form dy by dx is equal to f of x. And that's the easiest to deal with because I can just integrate both sides and say that y is going to be the integral of f of x dx. If a certain derivative is equal to a function, then y must be equal to the integral of that because the derivative is the opposite of the integral, antiderivative. So for example, if I had dy by dx is equal to x squared, then y would simply be the integral of x squared dx, which is x cubed over 3 plus c. Once you solve the differential equation, you're going to end up with a plus c, okay? And these plus c's are the constants of integrations, and therefore the solution that you get that contains the plus c is called the general solution. It's the, if you like, the family of functions that satisfies this derivative equation that we have, this differential equation. Oftentimes we'll be given an initial condition, which is the value of y for a specific x, which we can use to solve for c, all right? The result of that is going to be what we call the particular solution. So suppose we wanted to find the solution, or suppose we did find the solution, y squared is equal to c times e to the power of 2x minus 2 times x plus 3. And if we were told that the initial condition is y is equal to 2 and x is equal to 1, then I can figure out that I have 2 squared is equal to c times e to the power of 2 times 1 minus 2 times 1 plus 3. Or in other words, 4 is equal to c plus 3, and that means c is equal to 1. And therefore, the equation that I have is y squared is equal to x e to the 2x minus 2 plus 3. That is the answer, the particular solution. So the next most complicated differential equation that we need to now to solve is differential equations of the form dy over dx is equal to f of x times g of y. Now, when you are going to be given these equations to solve, they're not going to be obviously in this form f of x g of y. The point is that the terms that depend on x are separable from the terms that depend on y as a product, which means I can write the differential equation is dy by dx equal to something that depends on x only times something that depends on y only. And the advantage of these is that once you have these separated, I can divide both sides by g of y, and I'm going to get, and bring the dx to the right-hand side, and I'm going to get 1 over gy d of y is equal to f of x dx. And then I can integrate both sides, and I can find that the integral of 1 over g of y dy is going to be equal to the integral of f of x dx. So let's say I had dy by dx is equal to x squared over y. If I bring the y to the right-hand side, or to the left-hand side, and the dx to the right-hand side, I have the integral of y dy is equal to the integral of x squared dx. When I integrate y, I get y squared over 2, and when I integrate x squared, I get x cubed over 3 plus c. And so my solution is going to be, if I bring the 2 to the right-hand side and take the square root, y is equal to plus or minus the square root of 2x cubed over 3 plus 2c, also under the square root. So we're trying to solve the differential equation dy over dx is equal to y sine of x. And we're told that y is equal to 2 when x is equal to 0. That's an initial condition that we will use at the end. But first, what kind of differential equation do I have? Well, I have something that depends on y times something that depends on x. So I want to bring that y term to the left and bring the dx to the right-hand side. And I get something like 1 over y dy is equal to sin of x dx. And so now I put an integral in front of both of these. And the integral of 1 over y dy is ln of the absolute value of y. And on the right-hand side, the integral of sin is negative cos plus c. Now notice I didn't put a plus c on both sides because a constant on the right and a constant on the left can be absorbed into just one constant. You don't need to have multiple constants. They're not actually going to be adding anything new. Okay, so now how do I isolate y? Well, I raise both sides to the power of, I raise both sides in base e. So I do the absolute value of y is equal to e to the negative cos of x plus c. Okay, so that's what I have so far. And then I can apply my initial condition, right? And when I do that, I'm going to get, I should have y of 0 is equal to 2. So let's plug that in. When I have x equals 0, this becomes e to the negative cos of 0. Cos of 0 is 1, so negative 1 plus c should be equal to 2. Okay? So what does that mean? I can write this as e to the negative 1 plus, or times, e to the c should be equal to 2. All right? And therefore, that I can write that as e to the c is equal to 2e if I multiply both sides by e, right? Okay. So once I get that, I'm going to get, I can actually absorb, instead of writing the e to the c in the constant, I can actually just bring down e to the c because I have a sum in the exponents and write e to the negative cos of x times e to the c, which is 2e, all right? And this is the absolute value of y, so I'm going to say that, yeah, there you go. So the, I can say that y is going to be equal to plus or minus 2e to the negative, or 2e to the negative, and now I can bring the e back in, right? I can say that I have, I'm going to have 2e to the negative cos x plus e, so I'm going to have 1 minus cos x, 1 minus cos of x, okay? And that is my final answer. The next technique is the so-called integrating factor, and it's for differential equations that have the form dy over dx plus p of xy is equal to q of x. And we have this weird trick where we're going to multiply through by an integrating factor, mu. And essentially, this trick comes from the product rule, and you'll see that more clearly in the example. But by multiplying through by this e to the power of negative the integral of p of x, well, you would notice that if I take the derivative of, let's call this mu of x, if I take the derivative of mu of x, then mu prime of x is going to be the derivative of the exponent by the chain rule, so d by dx of the integral of p of x dx times the same thing, e to the integral of p of x dx, and the derivative of the integral of p of x dx, that is nothing more than p of x. Okay, so this becomes p of x e to the integral of p of x dx. And so the idea here is that we're going to identify a term when I multiply through by this. It's going to match up with the, when I multiply through by this, it's going to line up with the p of x such that this p of x, this whole term becomes the derivative of a product. And we'll see that in a second. I have a differential equation in this example, dy over dx plus 2x, plus 2y, sorry, is equal to 6. Okay, so what I have is the constant that's multiplying, or the function that's multiplying y here is just a constant 2. So p of x is equal to 2, which means the integral of p of x is equal to 2x. And therefore, mu is equal to e to the power of 2x. And here's what I do. I multiply the entire equation on both sides by e to the 2x. And I get e to the 2x dy by dx plus 2e to the 2x y is equal to 6e to the 2x. And now, this is where the trick pays its dividends. On the left-hand side, we can notice that we actually have the derivative of y e to the 2x as a product rule, okay? And that is why we specifically chose this this mu, such that I could, it was going to make both terms line up. So that I was going to get something times the derivative, dy by dx, plus something times the original p of x times y that I had earlier, okay? And the right-hand side hasn't changed, but now I have the derivative of y(e to the 2x is equal to 6e to the 2x. And this is always the hardest step, is spotting what derivative you took to arrive at the line above. So you're looking for, I have e to the 2x y prime plus 2e to the 2x y. I see that this is the derivative on one side by the product rule, and then maybe the 2 here is the derivative on the other side. And so I notice, okay, I have the derivative of y(e to the power of 2x. But it can be difficult to spot, and you should always check, okay, if I take the derivative of this, would it work? We can check quickly. Y(e to the 2x, when I take the derivative, is going to be y prime e to the 2x plus 2y(e to the 2x, okay? So it does indeed work. Now, once we have d by dx of something equal to something on the other side, I can integrate both sides. And then y(e to the power of 2x is the integral of 6e to the 2x. And 6e to the 2x when I integrate is just 3e to the 2x plus c, okay? And therefore y, the general solution, if I divide both sides by e to the 2x, is going to be 3 plus c e to the negative 2x. All right. So we're going to do another IB style problem here. All right, let's go over the solution here. In part A, we're trying to show a certain integral using a particular substitution. In particular, we want to use u is equal to cos of x. So first thing I'm going to do is I'm going to write the integral as, tan x is sin x over cos x. Okay. And I'm going to say u is equal to cosine of x, which means that du over dx is equal to negative sin of x, which means that du, or dx, sorry. Well, I can say this. I can say that du is equal to negative sin of x dx. And therefore, my integral can be written as negative du, because I don't have a negative in here, so I have to put a minus to cancel with this one. It's going to be negative du over now u, because cos of x is just u. And this integrates quite simply. This is going to be negative ln absolute value of u plus c. And I have u is equal to cosine of x, so it's going to be negative ln of the absolute value of cosine of x. And how do I make that into the secant? Well, I just put the negative inside as a power. I'm going to do ln of 1 over secant of x plus c is equal to ln, and sorry, 1 over cos of x ln secant x plus c. All right, that's my answer to part A. Now we're given the curve y is equal to f of x satisfies the differential equation dy by dx is equal to y tan of x is equal to sin x. All right, and we're told that f of x equals to 0. The question is asking us to show that mu equals secant of x is an integrating factor for the differential equation. Well, remember that the integrating factor is, it's going to be e to the power of the integral of p of x dx, where p of x is the thing multiplying x, so in this case, tan of x, all right? So it's e to the power of the integral of tan, and we just found out what that was. It's e to the ln of secant of x plus c. Now, when you're doing your integrating factor, your integral obviously is going to give you a plus c. And in fact, any plus c that you choose could give you a valid answer, but it's easier if you just pick the one where c is equal to 0 so that things stay a little bit cleaner. It's one less thing to deal with. But it would work if you chose a different c. You'd still be able to solve the differential equation. We just wouldn't get exactly the integrating factor that this question wants. All right, now I have e to the power of ln something. So ln is what power do I have to raise e to get the inside, and so this has to be the absolute value of secant of x. But because x is between negative pi over 2 and less than pi over 2, that means that cosine and secant are greater than 0, and so this is just secant of x, okay? And that is therefore the integrating factor. Now we'll move to part C. Hence find f of x. Okay, so now what I do is I take mu, which we said was secant of x, and I multiply through the entire equation by secant of x. So now I have secant of x dy over dx is equal to, sorry, not equal to, plus y, and I'm going to write tan x as sine x over cos x, times secant x, which is 1 over cos x, okay, is going to be equal to sine of x times secant, so 1 over cos x. All right. Now, let's simplify as much as I can. I'm going to have secant of x, secant of x, secant of x plus y, and I can actually just leave it. I'm going to leave it. This one is y tan x secant of x. I shouldn't have expanded it. Secant of x is equal to, now I have sine x over cos x. This is going to be tan x. And I forgot to put the dy by dx. It's secant of x times dy by dx. dy over dx. All right. Now let's remember that the derivative of secant of x is sec x tan x. And that is what I have here. So in other words, I notice that my differential equation can be written as d by dx of y secant of x, okay? And it's equal to tan of x on the right-hand side. And then I can say, therefore, that y secant of x is equal to the integral. I'm just integrating both sides here. Integral of tan of x dx. Okay? And we know what the integral of tan x now is. We said it was equal to ln of, and we don't need the absolute value because we're still in this range where secant is positive. So just ln of secant of x. Okay? And now if I just divide both sides by secant of x, I'm going to find that y is going to be equal to, dividing by secant x is the same as multiplying by cos x, so I can say it's going to be cos of x, and let's not forget the plus c here, we'll need it in a second, cos of x ln of secant of x plus c. Okay, now let's apply our initial condition. Y of 0 should be 0. If I plug in 0, cos of x becomes 1, so y of 0 equals 1 ln of, and secant of 0 is the 1 over cosine of 0, and that's 1 over 1, so that's 1 plus c. Now, ln of 1 of 0, so this is all equal to c, and that should be 0, which means that c is 0. So my final answer is y is equal to cos x, ln of x, ln of secant x, that is, ln of secant of x, and that's it. Okay, that's my answer. The next type of differential equation I want to talk about is what's called a homogeneous differential equation. And these are differential equations where the derivative dy by dx can be written as some function of y over x. And in general, these won't be immediately recognizable as functions of y over x. But if you're actually careful and you simplify as much as you can and isolate dy by dx, you'll always be able to find that you can express the derivative just in terms of the ratio y over x. All right. And when we have a function of y over x, what we do is we let y be equal to vx such that y over x equals v. Then we'll make the substitution in the differential equation. And whenever this is the case on the IB, they tell you to use the substitution y is equal to vx because sometimes it can be difficult to spot. So here's an example. Let's say I have y prime is equal to y plus x over x. All right. Now, if I were to simplify that, I would get y over x plus 1, which is indeed a function of y over x. In fact, the function would be f of x is equal to x plus 1. It's just that I have f of y over x. Okay. So I let y be equal to vx. And when I have vx, if I differentiate that, I'm going to get vx plus x divided by x because y prime is equal to y plus x over x. So I replace y with vx. And I get this vx prime is equal to vx plus x over x, and that's equal to v plus 1. Now what I do with this vx prime, the derivative of vx, is I use the product rule to differentiate that. I get v times the derivative of x, which is 1, so just v, plus x times the derivative of v, so x dv by dx, and that's equal to v plus 1. If I simplify that, I get x is equal to dv over dx, x dv over dx is equal to 1, and separating variables, that gives me the integral of dv is equal to 1 over the integral of 1 over x dx. I can solve that, and I'm going to find that v is equal to ln of the absolute value of x plus c. And remembering that y is equal to vx, I just multiply through by x, and I get y is equal to x ln x plus c, where c would have to be determined using the initial condition. So in part A of this problem, we're trying to verify by taking a derivative that the integral of secant of x dx is equal to ln of secant of x plus tan of x plus c. And it says verify by taking a derivative, which means I don't actually have to integrate. What I have to do is take the derivative of the right-hand side and make sure that it gives me secant of x, because if I were to take the derivative of both sides here, the derivative should cancel with the integral. So we're going to let y be equal to ln of secant of x plus tan of x. And the plus c is going to make no difference because when I take its derivative, it's going to be 0. All right, but I can still put it in here. I can say now that y prime is going to be, and the derivative of ln is 1 over the inside. All right, so 1 over secant of x plus tan of x. But this is going to be times by the derivative of secant of x plus tan of x. The derivative of secant of x is secant of x tan of x. And the derivative of tan is secant squared. All right, those are both in your formula booklet. Okay. And now, because I have secant of x in both terms, the numerator, I can factor it out. I have secant of x times tan x plus secant of x over secant of x plus tan x. But then I notice the term in brackets matches the denominator, so they're going to cancel. Okay, and therefore it's just going to be equal to secant of x. All right, and because I'm in the interval 0 up to pi over 2, I know that secant of x plus tan of x is never going to be equal to 0. All right, because both of them are positive in this interval. So that's part A. That's part A. And with that, we can try part B. And we're told to use the substitution y is equal to vx to solve this differential equation. So what I'm going to do is I'm first going to rewrite this differential equation, substituting in y is equal to vx. So I have x d over dx of vx is equal to, now y is vx, so vx plus x squared cosine, and y over x is just v, so cosine v. Now, the derivative of vx is going to be v times the derivative of x, which is 1, so v, plus the derivative of v times x, so x dv over dx. All right, that's equal to vx plus x squared cosine of v. If I expand on both sides, I notice that this xv cancels with this xv, and I'm left with x squared dv over dx is equal to x squared cosine of v. Now, in the question, I'm told that 0 is less than x. X is positive, so I can cancel these x squareds. They're not going to be 0. And then I can separate my variables, and I'm going to end up with 1 over cosine of v dv is equal to dx. And if I put an integral in front of both of these, that's what I have to do. And now all I do is I recognize that the 1 over cosine of v is the secant of v. And so I can say that I have the integral of secant of v is equal to, and the integral of dx is just x plus c. Now I know what the integral of the secant of v is. We found it in part A, or we verified it in part A. So it's going to be ln of the secant of v, and let's not forget there's supposed to be a dv here. It's my bad, I forgot the dv. Secant of v plus tan of v is equal to x plus c. And we're also told that y is equal to 0 when x is equal to 1. And so v, which is equal to yx, is equal to 0. All right, so if I plug that in, I get ln of secant of 0 plus tan of 0 is equal to x, which is 1, plus c. Now, the secant of 0 is 1, and the tan of 0 is 0. So I have ln of 1 is equal to 1 plus c, which tells me that c is equal to minus 1, because ln of 1 is equal to 0. So c must be minus 1. All right, now we're almost there. What I can say, therefore, is that ln of the secant of v plus tan of v is actually equal to x minus 1. And now if I exponentiate both sides in base e, it's going to cancel with the ln. I'm going to get secant of v plus tan of v is equal to e to the x minus 1, sorry. So this is secant y over x plus tan y over x is equal to e to the x minus 1. Okay, and that is my answer. Okay, another problem. Today is just going to be a lot of problems because there isn't that much theory to cover. Once we learn the methods, we learn the methods. Now we're just going to do a bunch of problems. So I will let you try this on your own for 5 minutes, and then I'll go over it. In part A, we're trying to show that y is equal to e to the x squared times the integral of f of x is a solution to the differential equation dy by dx is equal to 2xy plus e to the x squared f of x. Oh my God, what a mess. What a mess. Let's try and think about what this is saying. So I'm given a certain y that is supposed to satisfy a differential equation. So that means if I plug it in, it should actually work. So in particular, if I took d by dx of e to the x squared integral of f of x dx, I should get this right-hand side. So let's see if I do. Let's see what I get. I'm going to get the derivative of e to the x squared. It's going to be 2x e to the x squared times, again, the integral of f of x dx. This is the first left-hand side of the product law. I'm letting this equals u, this equals v. This is u prime v, and now I'm going to add u v prime, which is e to the x squared. And then the derivative of the integral part is just going to be f of x. That's the good news. So f of x, okay? Now let's simplify that. The e to the x integral of x, f of x dx is just y. So this becomes 2xy plus e to the x squared f of x. Okay, so that indeed does work. Perfect. Perfect. Now, that's verified, so I can clear my screen. And now part B is asking us to solve the differential equation, hence solve the differential equation. Dy by dx is equal to this. So let me expand what I have here. I have this is equal to 2xy minus e to the x squared times 1 over x. Okay, because I have an x that cancels with the one of them, but not the other one. Or I can write it as, let me just keep writing the dy by dx, 2xy plus e to the x squared times negative 1 over x. All right. Now, this is exactly the form that I have over here, except that f of x is equal to 1 over x in this case. So I say f of x, or negative 1 over x. And we already verified that a solution to that differential equation was y equals e to the x squared integral of f of x, so 1 over x dx. Now, when I integrate negative 1 over x, I take the negative outside, e to the x squared, and then I'm going to have ln of the absolute value of x plus c. Now all I have to do is use my initial condition, which is that y is equal to 0 when x is equal to 1. If I plug in x is equal to 1, or sorry, to minus 1 here, ln of the absolute value of minus 1 is the ln of 1, that is 0. I'm adding plus c and multiplying by e to the power of 1. So I have y is equal to negative e to the power of 1 times ln of x, ln of 1. I can just put ln 1 because I already put the absolute value. Ln 1 plus and plus c. Okay, and that should be equal to 0. Or in other words, I should have, well, ln of 1 is just 0, so this just goes away. And I have negative ec is equal to 0, which tells me that c is equal to 0. And so the equation, the solution, is just y is equal to negative e to the x squared ln of the absolute value of x. Okay? Basically, what we did was, in part A, we verified that this special integral was a solution to this in general for any f of x. And then we in part B, we had to use a special case of f of x to actually apply the formula we had in part A. So essentially what happened here is there are more advanced techniques for solving differential equations that you don't know or need to know. But the IB could and has, this is a sort of thing that has shown up on the IB before, ask you to essentially show that such a thing is a solution. Someone has figured out that this is a solution in general to equations of this form. You can show that relatively easily using derivatives, and then you can apply that to a different form. So the IB is kind of in one part teaching you a new way of solving a differential equation, and then asking you to apply it in part B. This has shown up once on the IB, so it's not exactly the super common question, but I wanted to make sure you had seen it. All right. Now we're going to talk about Euler's method, okay? And Euler's method is an approximation technique that we use for figuring out roughly what the solutions to a differential equation might be, or at least what the values of a certain solution might be. So when I have a differential equation of the form dy by dx is equal to some function of x and y, it depends on both of them, Euler's method enables us to estimate the value of y for a specific x by starting at a specific point that we know and taking small steps towards the x value where we are interested in. And it works like this. We start at the known point, which is here, and we find the slope at the current point. And then we take a horizontal step of size h, and we take a vertical step of size h times the slope found in 2. And we repeat that 2 to 5 times until each value is reached. So here's a little picture. We're starting with this point here, and we're going across each of these points, and we're just going some distance across in the x direction, following the slope of the function that I found. So I found a slope of 0, so I go straight across, and then I go down a little bit. It's going a little fast. I wish I could slow it down right now. But that's the idea. And you can see, I can move this and I can reset it. So let's see. It does the same thing from there. I can run it from here. And it's basically just gonna try and follow the slope of the curve. That's what it's gonna do. And we use this when we don't know what the actual underlying curve is. And in the IB, it's a common theme to ask you to use Euler's method first, then actually solve exactly, and then compare what your approximation is to what you know to be the exact value. So let's go over how exactly I would do this. What are the steps? So I start at a known point. Let's call it x naught, y naught. All right, the x naught, y naught. And I'm going to pick a step size. Usually it's given in the question, such that if I take x naught plus some integer n times my step size, I get to the final x that I want. So sometimes this question might say with 3 steps, and then you have to figure out what the step size would be. You're going to do x final minus x naught and divide by n. But you want to make sure that, for the right step size and the right step length, you're going to get to the final x that you're interested in. And what you're going to do is you're going to evaluate dy by dx. You're going to look at your differential equation, and you're going to figure out what the slope would be. And it'll be in the form dy by dx equals to something that depends on x and y. You'll plug it in. You'll find the slope. And the next x value is going to be x, in the first one is going to be x1. So x1 is going to be x0 plus the step size. And the y value is going to be y1 is equal to y0 plus h times the slope. So what I'm basically saying is, here I have some secret curve that I don't know. I'm at this point here. I measure that the slope is, roughly like this. So I figure out the slope is roughly like that. And I'm going to take a step size over here. I'm going to do a step of h, and then I'm going to do a step up of h f of x, y. So f times the slope. And you notice that I get exactly onto the line, not exactly onto the function. Okay, so that's why it's an approximation and not an exact technique. And I'm going to repeat that process with the new values of x and y at each step until I get to the final answer, until I get to the step that I want. So what does that look like? Let's say I'm given the differential equation dy by dx is equal to x to the power of y. And I'm told that y is equal to 1 when x is equal to 1. And I want to estimate the value of y when x is equal to 1.5 using a step size of 0.25. So let's start by saying that I have x naught, y naught is 1, 1. Okay, that's what I start with. And I find dy by dx at that point by plugging in 1 and 1, and that gives me 1. So the slope starts off as 1, which means my x1 is going to be x naught plus h. It's going to be 1.25. And then the next y is going to be, this is supposed to be y1, is going to be y naught, the starting y, plus my step size times the slope. It's also going to be 1.25. And now, at this point, I have to calculate what the dy by dx is again. I plug it back into x to the power of y, and I do 1.25 to the power of 1.25. Using my calculator, that gives me 1.32 approximately. And then I repeat my steps. Now, x2 is going to be x1 plus h, so it becomes 1.5. And y2 becomes y1 plus h times the slope that I just found, so 1.32. And y1 was 1.25. So I have 1.25
plus 0.25 times 1.32, and that gives me 1.62 on the calculator. Okay, so the point that I'm estimating is going to be 1.5 comma 1.62. Okay, so that's how you would do it in 2 steps. Usually on the IB, you will have between 3 and 5 steps to do, and they will always be with the calculator because the numbers are going to be ugly. All right, here's an example. I'm going to give you 3 minutes to get a head start on me, and then we will continue. The curve of y equals f of x is positive definite and satisfies the differential equation dy by dx is equal to y e to the x, and it's given that f of 0 equals 1. So the curve being positive definite means that f of x is going to be greater than 0, and we're going to need that fact later, but we'll put it aside for now. What I'm going to do is I'm going to construct a table to use for filling out Euler's method. So I need a table for the values of x, a column for the values of x, a column for the values of y, and then I need a first row for x equals 0, x equals 0.5, x equals 1, 1.5, and 2. So that's the table I have. So I'm going to put x, y, and y prime, starting at 0, 0.5, 1, 1.5, and 2. And I'm told that f of 0 equals 1, which means the original value of y is 1. And since dy by dx is equal to y e to the x, this is going to be 1 e to the 0 is equal to 1. All right. How do I calculate the value of y? Well, I'm going to do y0 plus y prime h, which is going to be 1, plus y prime is 1 times h is 0.5, 0.5 is equal to 1.5. Okay, so that's my second value of y. Now I calculate y prime. This time I'm going to be doing 1.5 e to the power of 0.5. I'm going to need my calculator to do that. So I'm going to do e to the power of 0.5 times 1.5. This gives me 2.473, and I'm going to keep more than 3 sig figs, so I have no rounding issues at the end. And therefore, this value here, the next y value is going to be the previous y value, so 1.5, plus y prime times h is 0.5, so 0.5 times 2.473. If I do that, 2.473 times 0.5 plus 1.5, I should get 2.7365. All right, and that means that now y prime is going to be 2.7365 e to the power of 1. So if I do that on my calculator, it's 2.7365 e, or 7.439. Okay? Next, I only have 2 steps left. I'm going to do 2.7365 plus half of what I just found, which is 3.719. So plus 2.7873665. This gives me 6.456. And therefore now my y prime for the last time is going to be 6.456 e to the power of 1.5, which is just going to be 28.93. And so finally, I'm going to do 6.456 plus 0.5 times what I just had, which is 14.47, plus 6.456, and I get my final value of 20.9 for f of 2 for y. Okay, so it's a very, very boring process. You just have to be careful, make sure you get your numbers right, and use your calculator effectively. Okay, now the interesting part is part B, solving the differential equation to find f of x. Let's remember that f of x is positive definite. What I'm going to do is I'm going to separate my variables, and I'm going to get 1 over y dy is equal to e to the x dx. And I can integrate both sides. And that's going to tell me that ln, absolute value of y, is equal to e to the x plus c. But because y is positive definite, y is going to be greater than 0, so I just have ln of y is equal to e to the x plus c. And now I can use the initial condition, which is x equals 0 and y equals 1. So ln of 1 is equal to e to the 0 plus c. Ln of 1 is 0, and this is 1 plus c, which means c is equal to minus 1. All right, so my equation now becomes ln of y is equal to e to the x minus 1, and so y is equal to e to the x minus 1. That is my final answer for f of x. Okay? So in part A of this problem, I'm trying to use Euler's method with a step size of 0.1 to approximate y of 1.2. I'm given that y of 1 is equal to 0, so I'm starting at x is equal to 1, and I'm using a step size of 0.1 to get to 1.2, which means I'm going to need 2 steps. So what I'm going to do is I'm going to add a row for 1, a row for 1.1, and a row for 1.2. And that's going to be x, y, and y prime. So I have x, y, and y prime. I'm starting at 1, 0, or 0, 1 actually, sorry. No, 1, 0, 1, 0. And that means that y prime is going to be 1 plus 0 over 1 minus 0, which is equal to 1. So when I get to x equals 1.1, I'm going to have 0 plus the step size, which is 0.1 times y prime, which is just going to give me 0.1. And now my y prime is going to be x, so 1.1 plus y, which is 0.1, over 1.1 minus 0.1, which is going to be equal to 1.2. All right, so when I get to x is equal to 1.2, I'm going to have 0.1 plus 0.1 times 1.2, which is equal to 0.1 plus 0.12, which is equal to 0.22. So that's my answer to part A. Now in part B, I'm trying to solve the differential equation using the substitution y is equal to vx, which means that d by dx, I replace this y with vx, it's going to be equal to x plus vx over x minus vx. Now, what I notice here on the right-hand side is that I have x times 1 plus v over x times 1 minus v. So I have x times 1 plus v over x times 1 minus v, and I'd like to cancel the x. So I can cancel them. X is not going to be equal to 0, so I can say 1 plus v over 1 minus v. Just put a note that x is not equal to 0. And therefore, now I have to differentiate the left-hand side, which is the derivative of vx with respect to x. So it's going to be v times the derivative of x, which is 1, plus x times dv over dx. Now what I can do is I can move this v to the right-hand side, and I can say that x dv over dx is equal to 1 plus v minus v times 1 minus v all over 1 minus v, which is going to be equal to 1 plus v minus v plus v squared, so 1 plus v squared over 1 minus v. And I can now separate my variables, and I'm going to get 1 over x dx is equal to 1 minus v over 1 plus v squared dv. I can integrate both sides. Let me rewrite what I have. I have the integral of 1 over x dx. Well, that's just ln of the absolute value of x, okay, which is equal to, that's equal to the integral of, and I'm going to split this into 2 parts. I'm going to say 1 over 1 plus v squared minus v over 1 plus v squared dv. All right. Now, the advantage of doing that is I can then say the integral of 1 over 1 plus v squared is arctan of v. I recognize that's in my formula booklet. And then the integral of v over 1 plus v squared, if I make a substitution u is equal to 1 plus v squared, I recognize this as minus half the natural log of 1 plus v squared. Now, because I have 1 plus v squared is a positive number plus a square number, which has to be positive, I can get rid of the absolute value and just write this. Okay? Let's not forget the plus c. So now I use my initial condition. I use my initial condition, which says that x equals 1 and y is equal to 0, which means that v, which is equal to y over x, is equal to 0. And so I have ln of 1 is equal to arctan of 0 plus half ln of 1 plus 0 squared, which is ln of 1, plus some constant c. Okay? Now, that can be written, arctan of 0 is just 0, and the ln of 1 is just 0, and the ln of 1 on both sides, so 0 on both sides, which means that I have c is equal to 0. Okay? Therefore, my final answer is going to be ln of the absolute value of x is equal to arctan of y over x minus half ln of 1 plus y squared over x squared, and plus c is just plus 0, so it stays like this. This is my final answer. And now we have a kinematics question in this next part. And we are told that a particle is moving in a straight line such that its velocity, v, in meters per second satisfies the differential equation dv by dt is equal to 4 minus v squared. Okay? So first thing I'm going to do is I'm going to solve this differential equation, and it's a separable differential equation. So I can write, I'm going to have dv over 4 minus v squared is equal to dt. Okay? Now, what can I do? If I integrate both sides, I can factor 4 minus v squared as the integral of dv over 2 minus v, 2 plus v. Okay, that's going to be equal to t plus c. And then I'm going to have to do partial fractions. I'm going to say that I have 1 over 4 minus v squared is equal to a over 2 minus v plus b over 2 plus v. And that should give me 2a plus 2b plus a minus b v all over 4 minus v squared. And that, in other words, tells me that 2a plus 2b is equal to 1, and that a minus b is equal to 0, because I have 1 for the constant term and 0 for the term in v. All right. Now, if I solve this equation, I have a is equal to b, which means that 4a is equal to 1, or in other words, that a is equal to 1 over 4. Okay, so now I can say my integral becomes the integral of, I put the 1 over 4 outside, it'll be easier. I'm going to have 1 over 2 minus v plus 1 over 2 plus v dv is equal to t plus c. And I can integrate both of those. It's 1 over 4. This one is going to be negative ln of 2 minus v in absolute value. And the next one is just going to be ln of 2 plus v. And someone is asking, what is b? Well, b is the same as a, so that means that b is 1 over 4. I should have made that explicit, but I found that a was equal to b. Okay, so that's all equal to t plus c. Now I'm going to multiply both sides by 4, and I'm going to use the difference of log rules to say that I have now ln of 2 plus v over 2 minus v is equal to 4t plus, and the c, I mean, I can write 4c, but it's a constant, so it doesn't really matter what it's being multiplied by. Okay, so that's already good progress. Now I can use the fact that the initial velocity is 0, because the particle is at rest. So if I plug in t is equal to 0, I should get, let me make like a bit of space. Let's erase this now. Okay, so when t is equal to 0, and v is equal to 0 as well, so I should have ln of 2 over 2 is equal to 4 times 0 plus c. The ln of 2 over 2 is ln of 1 is 0. So 0 is equal to 0 plus c means that c is equal to 0. So now, in other words, I have just, I can say that ln of 2 plus v over 2 minus v is equal to 4t, which means that 2 plus v over 2 minus v is equal to e to the power 4t. okay? And now I have to do a little bit of rearranging. And I'm going to say that I now have 2 plus v is equal to 2e to the 4t minus ve to the 4t. And I'm going to try and isolate all the v's together. So I have v times 1 minus, or 1 plus e to the 4t now because I bring it to the left-hand side, is equal to 2e to the 4t minus 2. All right, now I just do v is equal to 2e to the 4t minus 2 over 1 plus e to the 4t. And that is what I wanted to find, okay? So there we go. Now, let xt be the displacement in meters of the particle from the origin after t seconds. Show by evaluating integral that x of t is equal to ln of 1 plus e to the 4t over 2 minus 2t. Let's do it. So I know that the displacement is the integral from 0 up to from the start time to the end time, so in this case from 0 to t, and you have to be a little bit careful because my velocity itself is in terms of t, and I can't explicitly have the same t in the what's it called? Sorry, in the bounds as I do in the function. But it's not actually going to be that big of a deal. We just have to be a little careful when we're doing it, not to mix them up, right? And I can also actually just evaluate it without the bounds. But it is the integral, displacement is the integral from the start time, so t1 up to t2 of the velocity, v of t. All right. Now, in this case, my start time is 0, at which my start velocity is 0. So if I just integrate, I can integrate from 0 up to t. I can even just say, let's do the integral from 0 up to t of v of t dt, so I don't mix up. I have two different t's. And so let's integrate what I found in part A, which is 2e to the 4t minus 2 over 1 plus e to the 4t dt. Okay, I'm going to separate the integral such that I have one term that lines up with the denominator. So I'm going to have 2 times 1 plus e to the 4t. But now I have to subtract 4 to keep the same thing. 1 plus e to the 4t. So then I'm going to have equal to the integral of 2 dt minus the integral, or 4 times the integral of 1 over 1 plus e to the 4t dt. And this just becomes 2t minus, and now I'm going to say u is equal to 4e, and there's no 4, hang on, why am I saying 4? It's just e, sorry, if I let u equal to e to the 4t, so I say u is equal to e to the 4t, then du over dt is equal to 4e to the 4t. All right, and therefore I can now say that dt is going to be du over 4e to the 4t. Okay, or in other words, 4 over u. du over 4u. All right. Now I can rewrite my integral over here as 4 times the integral of du over 1 plus u times u. All right. And now that integral, and let's not forget there was a 4 in there. There was supposed to be a 4, so let's not forget the 4, and it's going to cancel with the 4 on the outside. I know this is complicated, but we're almost there. We're almost there. Now I have the integral, because the 4s are going to cancel, of du over 1 plus u times u. And I can use partial fractions to break that down, okay? So to use partial fractions, I have to do it again. I'm going to have a over 1 plus u plus b over u is equal to au plus b plus bu over 1 plus u times u, and I can immediately tell because I'm supposed to get 1 over u times 1 plus u, that I have b is equal to 1, and a plus b is equal to minus 1, or equal to 0, so that a is equal to negative b, okay? A is equal to negative b. All right, so that's helpful, because then I can say that this is going to be equal to, this integral is going to be just the integral of 1 over u minus 1 over 1 plus u du, which is equal to ln of u plus ln of 1 minus u plus c, if you like. Okay, now we're almost at the end. I can actually plug in what I know. The integral of v of t dt is equal to, and I can just do now 2t minus what I just found, so ln, I don't know why I put a 2, just minus ln of, and u was, u we said was e to the power of 4t, so ln of the absolute value of e to the power of 4t minus ln of 1 minus e to the power of 4t. And I'm not happy with it being, it's supposed to be a 1 plus, that's a 1 plus. And so this is actually supposed to be a minus. There was a mistake there. 1 minus, and so that becomes plus, okay? And there is a plus c that we don't know yet, okay? And so this becomes, I can write this as 2t minus 4t plus ln of 1 plus e to the 4t plus c, okay? Now, when I actually do the definite integral from 0 up to a certain time, what am I going to get? Well, when I have t is equal to 0, I'm going to have the t's are going to be 0, obviously, and I'm going to have 1 plus e to the power of 0 is going to be 2, actually. So I can say that I know that the initial position has to be 0. Okay, so if I plug in t is equal to 0, I get ln of 1 plus 1 plus c is equal to 0, means that c is equal to negative ln of 2. All right, so that's something I know. So I can now rewrite this as minus ln of 2, minus ln of 2, and that's going to help me because I can now rewrite the integral as ln of 1 plus e to the 4t over 2 using log rules minus 2t. And that is the result that I wanted to find, okay? That was a very difficult question there. So now we're trying to use the displacement of the particle, or find the displacement of the particle from the origin after t is equal to ln 3 seconds. So we have t is equal to ln of 3. So I have x of ln of 3 is equal to ln of, in a fraction, 1 plus e to the 4 ln 3 divided by 2 minus 2 ln of 3. Okay, so I'm going to get ln of 1 plus, and 4 ln 3 is ln of 3 to the 4 is 81. So e to the power of ln 81 is just going to be 81. That's going to be divided by 2 then, minus 2 ln of 3. Okay, so in other words, I have ln 81 plus 1 is 82, divided by 2 is 41, minus ln of 9 now, because I put the 2 in the exponent, and this becomes ln of 41 over 9. In this question, we're told that the population of salmon in the lake can be modeled by the differential equation ds over dt is equal to rs times k minus s all over 3k, where t is the time in year since 2019, s is the number of salmon in the lake, and r and k are positive constants. Okay, so the first thing I want to do is show that the derivative is going to be positive when s is less than k and negative when s is bigger than k. Now notice that rs over 3k are all positive constants because r and k are given to be positive constants in the question, and s is the number of salmon. That has to be positive. So rs over 3k has to be positive, and k minus s is going to be bigger than 0 when s is less than k, and it's going to be less than 0 when s is bigger than k. And because I have a positive multiplied by some term that is sometimes positive and sometimes negative, I can say that the whole derivative is going to be positive when s is less than k and negative when s is bigger than k. Now, hence explain why k is called the carrying capacity of the lake. So what I notice here is that if my population is currently below the value of k, if s is smaller than k, then the derivative is going to be positive, which means the population is increasing. And vice versa, if the population is currently larger than the value of k, then derivative is negative and the population is shrinking. So essentially what you have is a model where the population will always grow up to a maximum of k if it's below k, and will always shrink down to k if it is above k. And so k is the maximum number of salmon the lake can sustainably support, and the population will eventually grow to that maximum if given time to do so. Now in part C, I want to show that the maximum value of ds by dt is rk over 12. Now there's two ways I can do that. Either I can take the second derivative or I can take the derivative of ds by dt with respect to s, which would be very confusing, or I can recognize that by factoring out r over 3k, my expression for the derivative becomes r over 3k times s k minus s squared, which I recognize now this inside as a quadratic, and quadratics have a vertex, and that vertex is at x equals negative b over 2a, or in this case, s is equal to negative k over 2 times minus 1, which is k over 2. If I plug that back into my derivative, I get r times k over 2 times k minus k over 2 over 3k. Expanding that out, I'm going to get r times, this is k over 2. Inside the brackets, I have k minus k over 2, which is also k over 2. So I get k squared over 4, all being divided by 3k. And so this comes down to rk over 12, which is what I wanted. All right. Now, in part D, I want to solve the differential equation to show that s of t is equal to k over 1 plus a to the e to the negative rt over 3, where a is some positive constant. And it's important to note that we're told that in 2019, the population s is smaller than the carrying capacity k, which means the population should be increasing up to that maximum and not decreasing down to that maximum. Now, let's start by solving this. I have a differential equation that is separable. So what I'm going to do is I'm going to bring all the terms in s to one side. I'm going to have ds over sk minus s is equal to r over 3k dt, and I'm going to integrate both sides. Okay, now the right-hand side is pretty easy. This is just going to become rt over 3k plus some constant c. The left-hand side is a bit trickier. I have to use partial fractions. So I'm going to say that 1 over sk minus s is equal to a over s plus b over k minus s. All right, this a, small a, is not to be confused with this big A that we'll get to in a minute. Now, if I were to put those over a common denominator, I would have ak minus as plus bs, all divided by sk minus s. Now, I notice that my denominator here does not contain any s. In other words, I must have these two constants, or these two terms in s, be equal to 0. So that means that b minus a is equal to 0, or in other words, that a is equal to b. And I have the constant term, which is ak, just equal to 1, which means that a, which is equal to b, is equal to 1 over k. So now what I can say is that I have the integral. I'm going to put a 1 over k in front, and I have 1 over s plus 1 over k minus s ds is equal to rt over 3k plus c. And I can continue. I can integrate 1 over s. I know the integral of 1 over s is going to be ln of the absolute value of s. Because s is positive, it's just ln of s. And then I'm going to have minus the natural log of k minus s. And it's negative because I have a negative inside. So if I were to take the derivative and apply the chain rule, there's going to be a minus sign popping out of there. Okay? And I could put absolute value around k minus s. Technically, I should. But because I know that the population s is smaller than k, I can actually recognize that k minus s is going to be positive, so I don't need the absolute value. And this is all equal to RT over 3K plus C. Okay, now what I'm going to try and do is I'm going to, first of all, bring all the logs into one term, and I'm going to have ln of S over K minus S using my log laws. And I multiplied both sides by K here to remove the 1 over K. I'm just going to get RT over 3. And you can say plus CK if you want. Because C is a constant, it doesn't actually really matter. But let's leave it as CK for now. Okay, so what else can I do? I can now raise both sides to the power, or I can raise both e to the power of both sides, exponentiate both sides in e, and that's going to cancel with a log. So over here, I'm going to have s over k minus s, and it's going to be equal to e to the rt over 3 plus ck, which I can say is going to be equal to e to the rt over 3 times e to the power of ck, and I can just call that a. All right, so that's where my a is going to come in from. And now I just have to rearrange this into the form that the question wants, which is k over 1 plus a e to the negative rt over 3. All right, so what I'm going to do is I'm going to multiply both sides by k minus s, and I'm going to get s is equal to a e to the rt over 3 k minus s. Okay, so how many s's do I have? I'm going to have s and then plus s times a e to the rt over 3. And that is going to be equal to a e to the rt over 3 times k. You can factor out s over here. I have s times 1 plus a e to the rt over 3 is equal to k a e to the rt over 3. Now, isolating s, that gives me s is equal to k a e to the rt over 3 divided by 1 plus a e to the rt over 3. And it's almost what I want, except that in the numerator, I'm supposed to just have k, and in the denominator, I'm supposed to have 1 plus e to the negative something. And so what I'm going to do is I'm going to divide the top and the bottom by ae to the rt over 3. All right, so I can write that as now as k divided by, I'm going to have technically 1 over a e to the negative rt over 3, and then just plus 1. Okay? Now what I'm going to do is, I shouldn't have called this a because now it's a different a than what I want. I'm going to call this a prime. All right, a prime, because it's not exactly what I wanted. So these are all a prime. And now I'm just going to say that 1 over a prime is equal to a. Okay? Simplifying this, I am going to get k over 1 plus a e to the negative rt over 3. All right, and that is the answer I was looking for. By observing the population of salmon when food is unlimited, scientists know that the growth rate R is ln of 4. So R equals ln of 4. And the population of salmon is measured to be 1,000 in 2019. Now remember that t, this lowercase t, is the time since 2019. So in 2019, t is 0. So s of 0 is equal to 1,000. Okay? And that means that the expression I found, which is s of 0, is equal to k over 1 plus a, and then e to the negative 0 is just going to be 1, so it's 1 plus a. That's equal to 1,000. And I'm also told that the population in 2022, which is 3 years later, is going to be 1,500, and that's going to be k over 1 plus a e to the negative r, because t over 3 is just going to be 1 there, and that's supposed to be equal to 1,500. Now I have e to the power of negative ln of 4, all right? That's just going to give me e to the power of ln 1 over 4. So let me just write the e to the negative ln of 4 is equal to e to the power of ln 4 to the minus 1, which is just equal to 4 to the minus 1, which is equal to 1 over 4. All right? So my equation in the denominator is just going to be k over 1 plus ae over 4. So this is equal to k over 1 plus A over 4 equal to 1,500. Now, what I'm going to do to simplify these two is I'm going to eliminate k by dividing one equation by the other. I'm going to do s of 3 over s of 0 is going to be equal to, well, s of 3 has a k over 1 plus a over, so I'm going to do k over 1 plus a over 4 divided by k over 1 plus a. And that simplifies to 1 plus a over 1 plus a over 4. And I know that s of 3 is 1,500 and s of 0 is 1,000, so this should equal to 3 over 2. And if I cross multiply that, I'm going to get 2 plus 2a is equal to 3 plus 3a over 4. And that's going to allow me to say 2a I can say is 8a over 8, so 8a over 4, that is 5a over 4 is going to be equal to 1. And so a is equal to 4 over 5. Now, to find k, I can plug that back into here, for example. I can say that k over 9 over 5 is equal to 1,000, and therefore, k is going to be equal to 1,000 times 9 over 5. 1,000 over 5 is 2, and then times 9 gives 1,800, so k is equal to 1,800. And those are my answers. All right, so I'm just going to write those down because we're going to need them for the last part. K is equal to 1,800, and A is equal to 4 over 5. And we want to determine the population of salmon that were in the lake in 2600. And this requires a bit of a leap in reasoning to imagine that this model, this differential equation that was governing the population of the salmon, also applied in 2018 and 2017 and 2016. We're just imagining that nothing physically has changed in the lake. We just started sort of measuring the data that we have in 2019. And therefore, what we can do is we can take this model, right, which was derived, by the way, when we derived it, nowhere did we assume that the time was positive. We didn't do that anywhere. And so this model is actually going to work for negative times. So I can find s of negative 3. And that's going to give me k, which is 1,800, over 1 plus a, so 4 over 5, e to the negative r times t over 3, which is now going to be minus 1. All right, so this simplifies to 1,800 over 1 plus 4 over 5 ln, e to the ln 4. E to the ln 4, right? And I can use my calculator directly, but it's nice to do one more step and just say this is 1,800 over 1 plus 4 over 5 times 4. Okay, so what I'm going to do is I'm going to calculate 4 over 5 times 4 is 16 over 5. 16 over 5 plus 1 is going to give me 21 over 5, or 4.2. And I'm going to do 1,800 divided by that. And that is going to give me 428.5. So I'm going to round that to the nearest salmon. And I'm going to say 429 salmon. Okay. That was the last question I wanted to do today. So I'm going to stop my screen share and take any questions if you guys have them. Otherwise, that's going to be everything. So we're going to wrap up there. Thank you for coming again, and hopefully see you tomorrow for our last session on Maclaurin series. Anybody watching on the recording, I'm going to stop the recording now. So goodbye. Have a nice day.